All right, Unit 2 test review. I hope this review will help you as you're making your final preparations for the Unit 2 test. As you're doing this, I would suggest that you have your calculator, paper, pencil, eraser, periodic table, and a periodic table showing electronegativity, and that periodically you pause the video, practice the problems here, and then check your work. I have tried to double, triple check everything here to make sure that I don't have any mistakes because as you well know, it's easy to make mistakes on these types of problems. So let's get started. All right, so our first thing, carbon dioxide, shape and polarity. Great time to pause the video. All right, so what did you come up with? Hopefully you came up with carbon dioxide as a molecule looking like this, a linear molecule, because there's only two atoms attached to our central atom, no lone pairs, and that you came up with hopefully that it is a nonpolar molecule. It's nonpolar because if you look on one end, there's oxygen. On the other end, there's oxygen. Now, it's true that this bond is polar because carbon and oxygen are not sharing these electrons evenly. But because those electrons are being pulled towards oxygen, because it has a higher electronegativity of 3.44, that's going to make both ends of the molecule a little bit negative as those electrons are pulled towards the outside of both ends of this molecule. And so as you were taking a look at this, of course, CO2 is easy, but when you're given a covalent molecule with a name, you've got to be able to figure out what the formula is using the prefixes. All right, how about AlCl3? I've seen this mistake made multiple times. Hopefully you were thinking aluminum chloride. This is ionic, so there are no prefixes. Aluminum is not a transition metal, so no Roman numerals are needed. How about dinitrogen tetrahydride? Hopefully you were thinking N2H4. And how about chromium sulfate? I do apologize. This is chromium 4 sulfate. See if you can get to the answer at the bottom. And so hopefully you were thinking, okay, chromium 4 means Cr plus 4, and sulfate is 2 minus. So if we use our crisscross rule, we come up with Cr2SO44, and then we have to reduce that. Because obviously to equal 0, we don't need 2 chromiums and 4 sulfates. All right, this is another great time to pause the video and check how you can do on these 4 problems. So these are molar conversions. In the first one, of course, you're converting moles to grams. Or I'm sorry, you're converting grams to moles. It's saying how many moles are in 45.3 grams. And then moles to particles. So pause the video and check how you did. Great. So for these, it would not accept my text boxes to give the whole problem out. So I am just giving you the answer. And so for the first one, how many moles in 45.3 grams of iron chloride? When I worked this one out, I started with 45.3 grams of iron chloride and then divided by the molar mass of iron chloride. And of course, this is going to be iron 2 chloride, which I came up with as 126.745 to get 0.3 moles of iron 2 chloride. All right, how many grams are in 8.32 moles of water? I came up with 150. I put that decimal point there so that you would be aware that we need 3 significant figures. So once again, I took 832 moles, then I multiplied by the molar mass of water, which is 18. Okay, moles to particles. For these, I had to use Avogadro's number. And so if I have 5.42 times 10 to the 22nd atoms of oxygen, I simply multiplied by 1 mole over Avogadro's number to get my 0.09 moles of oxygen. And the last one, hopefully you came up with that number of molecules. Remember, you're typing those numbers in scientific notation into your calculator. Instead of typing in times 10 right here, you do type in second function EE. Oh dear, one of them is already up here. So moles to liters, liters to moles. Don't look at that answer down there. Pause the video and see what you can do. So for moles to liters, I used the ratio of 22.4 liters equals 1 mole and simply multiplied 6.99 times 22.4. How many moles are in 882 liters? So for this one, 882 liters, I multiplied that by the fraction of 1 mole over 22.4 liters. So in other words, dividing 882 by 22.4. Now, keep in mind that if you're converting from moles of one chemical to moles of another chemical, you would use your balanced chemical equation. That's the only time you need to use that equation. So, see if you can answer this question right here with copper and silver nitrate. All right, let's see how you did. And so as you're doing this, hopefully you were noticing that your moles of copper canceled out or diagonally dropped. So we've got 22.8 moles of silver produced. All right, what would you say for the answer for this one? Hopefully you were thinking this one for the decomposition of dinitrogen tetrahydride. Okay, how are you on drawing Lewis structures? Remember, they only show the valence electrons. And so you could draw these for a single atom like chlorine. Did yours look like this? Hopefully it did. Keeping in mind that chlorine, of course, has a high ionization energy and a high electron affinity. And what rule states that chlorine is going to gain 1 electron to fill its valence shell? Hopefully you were thinking the octet rule is the one that we're looking for there. All right, chemical bonding, 2 types of bonds. Anytime you're asked about a type of bond, your only choices are ionic or covalent. So you should write that down, memorize that. Anytime we ask for a type of bond, ionic or covalent only. All right, remember the ionic bonds, electrons are transferred. You name the metal first, followed by the non-metal and IDE. In covalent compounds, the electrons are shared, so the naming is very simple, but prefixes are used. So, how about potassium and iodine? What kind of bond occurs, and what would the formula be? How would you show this? Great time to pause the video. All right, hopefully you got something like this, that potassium has that 1 valence electron that it's trying to give away. Iodine is going to accept it, so we get a formula of Ki, potassium iodide. How about sulfur and calcium? And what kind of bond occurs here? Now, did you notice in this one, I put the sulfur first and expect you to be able to know that the metal needs to come first. Of course, calcium has 2 valence electrons that it's trying to give away to become a 2+ ion, and sulfur has 6 electrons. I apologize, a couple of my electrons, it looks like, have moved. And so it's going to gain 2 to become a 2-. And so what would be the name for this compound? Hopefully you were thinking calcium sulfide. The metal followed by the non-metal with an IDE ending. And again, no prefixes are needed. How about iron 3 and nitrate? Hopefully you used your crisscross rule and you came up with FeNO3. And what would the name for this be? Because iron is a transition metal, you will need the charge of iron in parentheses. Don't forget the characteristics or properties of both ionic and covalent compounds. Ionic compounds tend to form a crystal lattice. They often separate to form ions. We also know them as electrolytes when dissolved in water. They do have high melting and boiling points, whereas our covalent compounds are only the nonmetals. We draw Lewis structures for these, and they typically have low melting and low boiling points. All right, what about the covalent bond between H and Br? What would its shape be? Is it polar, nonpolar? All right, so how did you do? So that's one way to draw this Lewis dot structure. And so to figure out the polarity, of course, look at your table of electronegativity. I've got our H and Br with an electronegativity difference of approximately 0.9, which means it's going to be a polar molecule. It's also going to be linear in shape. And it's because it has H on one end and Br on the other end, and Br is more electronegative, the Br end is going to have a slightly negative charge, with the H having a slightly positive charge, just like this. And so we call this a polar molecule, or sometimes known as a dipole, because there are two poles. And what would its name be? Hopefully you were thinking hydrogen monobromide. We just don't use the mono in the front. All right, practice with these four. Again, a great time to pause the video, and let's see how you did in just a moment. All right, so boron trifluoride. Oh, I should tell you, no octet for boron. Did you come up with something like this? Coming up with the fact that it's trigonal planar and nonpolar. Sulfur dichloride, SCl2. Hopefully you came up with something like this, that it has, and I don't know if you can see it down at the bottom there or not, that it has a bench shape, and it is polar. How about carbon tetrafluoride? Hopefully you came up with something like that, with a tetrahedral shape and nonpolar. And beryllium difluoride, so BeF2. Again, no octet for beryllium. And it is linear. The bonds here are very polar, but the molecule itself, because it's got F on both ends, is going to be nonpolar. All right, here's a little practice for naming compounds and identifying the type of bond. Remember, when we say type of bond, we mean ionic or covalent. All right, so let's see how you did. Hopefully you got sodium oxide, ionic. Oh, iron 2 chloride. Let's see, where's our nitrogen? Oh, and that is incorrect. Oh, and I didn't catch that. This should be dinitrogen, because there's two nitrogens, monoxide. And it is covalent. So make sure you make a note of that. How about ammonium sulfate, carbon tetrafluoride, aluminum bromide being ionic, copper 2 oxide, because again, this copper would have had to be a 2+, because we know oxygen is always a 2-. So in order for them to equal out, this copper has to be a 2+, making it copper oxide, copper 2 oxide. How about dinitrogen tetrahydride? All right, can you practice writing some formulas? Again, another place to pause the video. Hopefully you got MgSO4 for this ionic compound. How about you got P2S3? How about hydrogen sulfate? Hopefully you got H2SO4. For tin, hopefully you got SnNO3 2. N2O, dinitrogen monoxide. How about SnClO3, 2? Because you would cross those charges, the 4 and the 2, and then reduce. Did you get IBR3? Great. Now, when we are writing formulas, we're often, especially in an ionic formula, confronted with something like NH4 that has a 1+ charge named ammonium, or SO4 with a 2- charge that's called sulfate. What are those? Hopefully you were thinking they are polyatomic ions. Now, as we're looking, these polyatomic ions, by the way, are all nonmetals, so they are covalently bonded, and the shape is very important for these molecules. If you have two formulas that are the same with different shapes, like you see here, they are called isomers. Both C4H10, tetracarbon decahydride. Also, as we're thinking about the shape, I would try to commit this chart to memory. I think it's very helpful for working with and figuring out shapes. Speaking of shapes, can you draw sulfur dioxide? Hopefully you came up with something that looks like this, and that it's a polar molecule. And hopefully you were thinking it was a bent shape because of the lone pairs of electrons. Don't forget, it's those lone pairs of electrons that affect the shape of the molecule. And that affects the shape of the molecule when the lone pairs are attached to the central atom. All right, hopefully you're looking at this one and knowing that it's linear. How about phosphorus trichloride? Can you draw that? Hopefully you came up with something like this, and you know that it is trigonal pyramidal. And it is going to be polar. Our difference of electronegativity, the structure of our molecule allows the top half of the molecule with phosphorus and its electronegativity of 2.19 to be partially positive, and the chlorine end partially negative. And what do we call those electrons there? Hopefully you're thinking those are called our lone pairs. Just a couple tricks I would suggest when you're working with the covalent compounds, you use that honk rule. Remember, every hydrogen needs 1 bond, oxygen 2, nitrogen 3, carbon 4, and then that chart that I just showed you earlier. When you have multiple bonds, don't forget how many electrons are shared. So in this single bond, that's 2 shared pairs of electrons. In the double bond, which is shorter and stronger, 4 shared pairs of electrons. Take a moment and see if you can figure out the shape for each of these. Hopefully you came up with linear, trigonal pyramidal, and linear. Don't forget the intermolecular forces that allow particles to stick together. If it's within an atom, within a compound, a molecular compound or an ionic compound, then they're called intramolecular forces. But if it's between two different compounds, it's called intermolecular forces. All right. And how are we on chemical equations? Don't forget that the reactants become products, like shown right here. And so our products, that might be a question that I ask on the test. What are the products? And so I would be expecting you to say magnesium carbonate, solution, and solid aluminum metal. What are the reactants in this equation? Hopefully you were thinking aluminum carbonate or aqueous aluminum carbonate, and then solid magnesium metal. Here's another one that we can take a look at. Is this reaction balanced? Hopefully you were thinking, no, it's not, because we have to still add those coefficients. You also need to be able to recognize the various types of reactions, like this one right here is synthesis or combination because we have a single product. How about this one? Hopefully you were thinking single replacement because there's a single element on each side. On the reactant side, we have C. On the product side, we have B. Can you predict the products for this reaction? This again is a single replacement reaction because on the reactant side, our single metal is zinc. And as that zinc comes in and kicks out the copper, then copper is going to be the single metal. How about this one? Two elements reacting. So they must form one product and be a combination or synthesis reaction to get FeCl3. And of course, we're going to need to balance this by adding some coefficients. Can you predict the products for this reaction? Keep in mind that this would be an oxidation reduction reaction. Notice that over here iron 3 is a 0 and it becomes a 3 plus. So it's being oxidized even though it's not combining with oxygen, it's combining with chlorine. So here's how you work this out to figure that out. All right, what type of reaction? Hopefully you're thinking with the single reactant that it's got to be a decomposition reaction. And this one? Hopefully you were thinking a double replacement reaction. And this one? This one seems to be really, a lot of people seem to be struggling with these combustion reactions. Where you have a fuel and oxygen producing CO2 and water. How about this reaction right here? What would be your products? Well, it's exactly what I just said. You have a fuel and oxygen forming CO2 and H2O. And in order to balance it, you're going to have to add some pretty big coefficients. And that's the case with many combustion reactions. How about this one? Hopefully you were thinking that is a double replacement reaction, an acid-base reaction. What would you say this one is? Hopefully you were thinking double replacement reaction with the solid precipitate here being produced, so also called a precipitation reaction. And so as we're looking at these double replacement precipitate reactions, copper 2 sulfide here is our precipitate. And so remember, we can write the net ionic equation in order to get to the copper 2 sulfide, which is our precipitate. We really need the sulfur or the sulfide ion and the copper ion. We don't need these others. They are simply spectators. And so we can write our net ionic equation. All right. And then we've worked on using chemical quantities in reactions. This is stoichiometry, because when reactions are written, they're written in terms of moles. Remember that if you have a mole, you can convert to particles, and you do need to know what this number is. Hopefully you were thinking, oh, that's Avogadro's number. You're right. We use those moles to represent the quantities of chemicals in reactions. So these coefficients represent 2 moles of nitrogen monoxide and 2 moles of nitrogen dioxide produced. And so there's lots of conversions you can do once you have moles. So make sure you're familiar and comfortable with those. And so if we have an oxygen tank with 0.426 liters, how many grams of oxygen can the tank hold? Great time to pause the video and practice this one. Always start with what you're given. No different than any problem we've been doing all year. So that's where we're always going to start. I'm seeing some of you still forgetting that this is just a placeholder. Then, of course, using this 22.4 liters is equal to 1 mole. We're going to convert from liters to moles. Then using our molar mass for oxygen, we're going to convert from moles to grams. Go straight across the top and multiply. 0.426 times 1 times 32. And then 1 times 22.4 times 1 on the bottom. Then divide. And you should have hopefully come up with 0.609 grams of oxygen, rounded to 3 significant figures. All right, here's another one. These little wound sticks that some doctors' offices still use. They do put about 0.0013 moles of silver nitrate. So how many grams would that be? So when you're going from moles to grams, hopefully you're thinking you've got to use your molar mass from the periodic table and write the formula for silver nitrate correctly. So a great time to pause the video and see if you can do all of that. So hopefully you've got the molar mass for silver nitrate, started with your given, and multiplied by your molar mass. All right, how about if you're doing a mole to mole conversion? Do you remember how to do that? Hopefully you're thinking, yes, must use the balanced equation. So how many moles of O2 are produced when 3.34 moles of Al2O3 aluminum oxide decomposes? Hopefully you were thinking, start with what you're given, look at the equation for your mole ratio, and multiply across the top. 3.34 times 3 divided by 2, and you get 5.01 moles of oxygen. And that way, if you know anything, the chemical in the reaction, you can find all the other chemicals, and you can use your conversions to find those chemicals in liters, because 22.4 liters is a mole. You can find them in particles because of Avogadro's number, or you can find them in grams because of the molar mass from the periodic table. And so as you're looking at this equation, every time we use 2 moles of Al2O3, you're going to always make 3 moles of O2. And so that can be written as a conversion factor. Sometimes I call them conversion factors. Sometimes I call them fraction style ratios, to write those and to cancel out whatever you need. We've also done a lot of mass to mass stoichiometry problems. We did that in lab 6. So for example, making laughing gas for a dentist office, they take ammonium nitrate and allow it to decompose. So what mass of ammonium nitrate is required to make 33 grams of dinitrogen monoxide? In other words, laughing gas. Great time to pause the video and see if you can get to the correct answer. All right, how did you do? Hopefully you first balanced the equation, then you converted your grams to moles with your molar mass, then moles of one chemical to moles of another chemical with your equation, because 1 mole of ammonium nitrate equals 1 mole of dinitrogen monoxide. And there's our molar mass of ammonium nitrate. Go straight across the top and multiply. Go straight across the bottom and multiply. Then divide your top by your bottom. So there it is. And hopefully you got 60.342 grams of ammonium nitrate. And I've reduced for significant figures. And keep in mind that as you're going through and doing all of these calculations, what is that number called? That is your theoretical yield. In the lab, you're probably not going to get that. What if we only made 45.1 grams of laughing gas? and we thought we were going to make 60.3, what would our percent yield be? And so again, you would take your actual divided by your theoretical times 100. And so we've got a percent yield of 74.8%. Here is another one that you can try on your own if you get to this point in the video. Let me know if you can figure this one out. I do have a video for this one as well, and I'd be happy to share that with you if, in fact, you want to try that one. Otherwise, I think this wraps up everything you need to know for your Unit 2 test. I wish you great luck.